Nripesh Kumar Mandal, retired professors of statistics, Calcutta University. I will talk on optimum design. This is part of design of experiments. What do you mean by design of experiments? Let us first explain what we mean by design of experiments. In an experiment, there is a response which depends on a number of explanatory variables, and purpose of the design is to find a relationship between this response and the explanatory variables. This is what is, in other words, it is used to find a cause and effect relationship. Now, in this design of experiments, this is based on a model, its analysis and interpretation. There are different components, construction of standard designs, and thirdly optimum choice of design of experiments. Now, these are all well known, analysis and interpretation as well as construction of designs, and I will mainly concentrate on optimum design of experiments. There are two distinct setups, one the discrete domain and the other one is continuous domain. In the discrete domain, the factors depends on a number of quantitative factors at distinct levels. As for example, the yield of a product, yield of crop, say paddy, that depends on the varieties of paddy, depends on soil, depends on manure, etc. So, there are a number of factors which influence the response under study. Similarly, in the continuous domain, the growth of a tumor, that depends on the different pathological or different characteristics of the patient, say blood pressure, sugar, etc., the body weight, prior history. So, we will have different types of problems depending on the different setup. Now, there is a third one which is a combination of both. I will mainly talk on the first one and then the continuous domain. Discrete domain, the experimental design is concerned with the allocation of treatments. So, in the paddy, say different kinds of seeds, we have a number of plots. How to allocate the different seeds to different plots, that is that depends on different, that gives different responses. So, the problem of designing is that of allocation of treatments or different kinds of paddy to different plots. The objective in design of experiment is that of choosing the best variety, that is to compare the performance of different paddy, which one is the best paddy. Here we are concerned with the optimal choice of the design, that is how to choose the best possible allocation of different paddy to different seeds, to different plots. That is the, now there are standard designs, what is called randomized block design, Latin square design, balanced incomplete block design, partially balanced incomplete block design. The analysis, construction, these are all well known, but how or why we should use these optimal designs, RBD, LSD, etc. That is the question talk on here. So, there are say n experimental units and there are V blocks, each of sizes say sizes K1, K2, Kb, and there are V treatments or V say V kind of seeds. We want to compare the performance of these designs. How to allocate the different treatments to different plots, that is our question. In general, we can write this in the ijth cell, say ith block and jth treatment we allocate. Then the model is like this, the response y. In statistics, everything is random, probabilistic. So, this yij that can be written, or we want to model this in this form, y ij u equal to mu plus beta I plus tau j plus eij u. This mu is the general effect, beta is the effect due to ith block, tau j is the effect due to jth treatment, and eij u is the random error. It has a distribution which has mean 0 and homoscedastic independent with variance sigma square. Now, the general model is like this, y equal to x theta, that can be written in this form. Now, the matrix notation, in matrix notation we can write this in this form 1 d1 d2 x, and theta is the parameter vector, that is mu beta tau, and our problem is to estimate this mu beta tau, on the basis of which we can compare the performance of different tau j's. Now, incomplete block design, in many situations it is not possible to accommodate all the V treatments in a single block. That is why we have to use the incomplete block designs. Now, within these incomplete block designs there is a different types of questions, that it may not be possible to estimate all the coefficients, all the parameters or all the contrasts. A design for which we can estimate all the parameters is called connected design. We will restrict to connected designs, because we want to compare the performance of the different treatments. Now, for any parametric functions h prime tau, which is a parametric functions involving treatments in which we are interested, the best linear unbiased estimator is h prime tau hat, where tau hat satisfies this C tau equal to q. This is what is called C matrix, is called the characteristic matrix of the design. This is very, very important in design of experiments, because this characterizes the design. Now, the structure of C matrix is like this: C j j prime is R j delta j j prime minus summation n I j prime by k I, where R j is the replications of that treatment, n I j is the incidence of the jth treatment in the ith block, that is how many times jth treatment appears in the ith block. K I is the size of the ith block. Q is the vector of Qj's, where Qj is the adjusted treatment total. Capital B I is ith block total, capital T j is the jth treatment total, and G is the grand total. Based on this, we have the structure of C. Now, we restrict to connected designs, as I have said, because we want to estimate all the contrasts, on the basis of which we can select the best design. Now, first of all, there are two kinds of criteria which we shall consider mainly. That the first one is set of all elementary treatment contrasts, that is all possible tau j minus tau j prime, and there is another one which is called orthonormal treatment contrasts. First of all, let us consider elementary treatment contrast, all elementary treatment contrast. In 1956, Kempthorne started this problem. He first of all defined the efficiency factor of a design. Efficiency factor of a design is defined as the ratio of average variance of an RBD relative to the average variance of the proposed design. So, this efficiency factor is in fact always less than or equal to 1. A design for which this efficiency factor ED is maximum is called the most efficient design. Now, Kempthorne in 1956 Annals of Mathematical Statistics, he find an expression for this efficiency factor ED, that is V by n into D, this one V by n into D delta, where delta is the harmonic mean of the non-zero eigenvalues of the C matrix of the design. So, what we see, though there are different types of functions T j, B I etc., but this efficiency factor only depends on the characteristic roots of or eigenvalues of the C matrix of the design. That is why C matrix is called the characteristic matrix of the design, because this characterizes the design. Now, Kempthorne, he find an expression for this efficiency factor, which is V by n into delta, but he did not explore how to get the most efficient design. J. Roy of Indian Statistical Institute in 1958, Sankha, which is a journal published from Indian Statistical Institute in 1958, he showed that this delta is a maximum for certain designs. He characterized these optimum designs based on this criteria V by n into delta. He showed that delta is a maximum when the design is an RBD, when the design in the class of incomplete block designs, connected incomplete block designs, the design is BIBD. So, a very important result due to J. Roy, that a design which is most efficient in the class of incomplete block designs is in fact a balanced incomplete block design. A balanced incomplete block design is an arrangement of V treatments in B blocks each of size k, such that each treatment is replicated equal number of times R, and any pair of treatments appear in the same blocks lambda times. That is the definition of BIBD. This is the result which is obtained by. Now, next one, as I have said, the one is all element treatment contrasts and the other one is we can consider orthonormal treatment contrasts. Let us consider an orthogonal matrix L, whose first row is a multiple of 1s, all 1s, and the rest, that is a V minus 1 by V matrix P. This satisfies these conditions, P 1 is null, P P prime is I V minus 1 and P prime P is this thing. If we consider psi equal to P tau, then this psi represents a full set of orthonormal treatment contrasts, because with V treatments there can be at most V minus 1 contrasts, and P, since P P prime is I V minus 1, it means all the contrasts are orthonormal, not only orthogonal, but orthonormal. So, we will talk on the optimality of designs for this psi when we are interested in a full set of orthonormal treatment contrasts. Now, if we use a design psi, then with this design we have the estimation of parameters and hence tau hat, and once we get tau hat we get psi hat. It is unbiased with variance this. This P C prime P prime inverse into sigma square, that is the dispersion matrix of psi hat, and we will either we can minimize this variance or dispersion matrix, or we can maximize the information matrix, its inverse P C P prime. Now, what do we mean by maximization or minimization of a matrix? It is a very, very tall task. It is very difficult to maximize or minimize a design. Now, two designs, say two information matrix A and B, how we can order them so that we can maximize this. Now, one possibility is that of lower order domination, where A is greater than or equal to B means that A minus B is non-negative definite. Non-negative definite means that all the characteristic roots are greater than or equal to 0, non-negative. Similarly, the other way. Now, such an ordering, what we call lower order domination or partial lower ordering PLO, is very difficult. We will show that even in the simplest setting it is not possible to find a lower based design. So, the research workers who are working on this, mainly Kiefer, he developed a number of criteria. The most commonly used criteria are ADE optimality criteria, which are some functions of this. Now, A optimality criteria, D optimality criteria and E optimality criteria. A optimality criteria means the minimization of trace of the dispersion matrix, D optimality criteria, the minimization of determinant of this thing, covariance matrix, and third one is E optimality criteria which maximizes the minimum characteristic roots of the dispersion of the information matrix or minimizes the maximum characteristic roots of the dispersion matrix. These are the three well known criteria. The first criteria in fact minimizes the average variance of all elementary treatment of all contrasts. D optimality criteria minimizes the generalized variance, and third one, it has statistical significance that it minimizes the maximum variance of C prime theta hat. Now, details about this can be found in Kiefer 1959 and Sina 1989. And there is another optimality criteria called Phi P optimality criteria, that is also developed by Kiefer. The main contributor is in fact in this area is Kiefer. Now, the Phi P optimality criteria, that is a generalizations of this ADE optimality criteria, that is defined in this way. Say lambda is are the characteristic roots of the information matrix, then phi t of the information matrix is 1 by p summation lambda to the power t whole to the power 1 by t, and for different particular choice of t we get A, D and E optimality criteria. Now, it can be shown that a design is D, A and E optimum in the block design setting if all the non-zero characteristic roots of the C matrix are all equal. To get an idea about the proof of this result, let us consider the optimality criteria. Here we want to maximize the minimum characteristic roots of lambda, that is lambda 1. If we order the characteristic roots of P C P prime, this is 0 greater than lambda 1 less than equal to lambda 2 etcetera less than equal to lambda v minus 1. In selecting the design, the one approach is that of maximization of the minimum characteristic roots of the information matrix, that is PCP prime, or equivalently to minimize the maximum characteristic roots of its inverse. Now, the characteristic roots of PCP prime is ordered in this way, while that of PCP prime inverse is 1 by lambda 1 greater than equal to 1 by lambda 2 etcetera. So, if we want to use the E optimality criteria, we have to maximize lambda 1. Now, this lambda 1 is less than equal to, because of those inequalities of the characteristic roots, lambda 1 is less than equal to summation lambda v minus 1, and that is the trace of the matrix. Now, equality holds if and only if all lambdas are equal. This establishes the optimality of the block design. Similarly, using harmonic mean, arithmetic mean inequality and geometric mean arithmetic mean inequality, we can establish the optimality of a design for which all lambdas are non-zero lambdas are equal. This establishes the optimality of BIBD again, balanced incomplete block design, which we have seen holds for all elementary contrast by J. Roy. So, we get this theorem that in the class of connected proper incomplete block designs, a BIBD if exists for a given B, V and K is A, D and E optimum in the whole class of designs. Now, if exists means that given a set of parameters, a BIBD may not exist. There are a number of results on the existence and construction of BIB designs. Main contributor is of course R.C. Bose, Raj Chandra Bose, who was once after P.C. Mohanlal, who was the head of the department of Calcutta University, Department of Statistics. In the row column design next, there are two elimination of heterogeneity, one along rows and the other on columns. In this setup, Kiefer shows that again that a Latin square design and a Newton square design, they are optimum with respect to A, D and E optimality criteria. Now, next Kiefer introduced universal optimality criteria, and with respect to this universal optimality criteria, Kiefer again established the optimality of BBD, balanced block design and generalized Newton design. Next, I pass on to continuous domain. As I have said that the first one is discrete, that we are comparing a number of varieties, say discrete. Domain is discrete, while in the continuous domain, say the temperature varies in continuous domain, pressure varies in a continuous domain. So, here the selection is that of a point in a 2-dimensional geometry or n-dimensional geometry. So, here there are infinite number of designs. How to select a design? There are two parallel approaches, one by Box, GEP Box, the other one by again Kiefer. Box was concerned with developing methodology for tackling practical problems, applied problems, while Kiefer, he used the mathematical theory for finding optimum designs. I am first talk on the approach of Kiefer. Consider a regression setup. The response y, it depends on number of explanatory variables x, x depends on a domain, continuous domain, and fx theta, and this is the error part. Now, this is the modeling. How we explain this fx theta? There are different kinds of model, linear model, nonlinear model. We will talk here on linear model, that is fx theta can be expressed as f dash x theta, this one. This is the explanatory variables, theta is the parameter vector. Now, in the regression models, simple case, linear regression alpha plus beta x plus gamma x square. This is the linear, the second one is quadratic, but quadratic in x's but linear in parameters, that is why it is called linear model. If we have k independent variables, the model will be like this. So, in general we write this eta x as f dash x theta. So, f dash x for different model, f dash x can be written in this form, and a design for k independent variables is given by this one xu1, xu2, xuk. If we have n design points, u equal to 1 to 2n, and model can be written in this form. An example is this. Say interested in theta or a theta hat, then dispersion of a theta hat by least square theory is sigma square a x prime x inverse a prime. Let us start with a very simple example, say theta naught plus theta 1 x, then x prime x becomes this, and this m is called the per observation basis x prime x. If we want to compare two designs, if we have of different sizes n1, n2, how to compare this design? If we add new design points, new information, we always have a greater information matrix. So, it is better to compare two designs on the basis of per observation basis. That is why this is the information matrix on a per observation basis. So, how to find this information matrix M, which is maximum? As I have said, that it is very difficult to find a design which is lower or better in the matrix sense. Suppose we want to compare two designs. Now, to maximize this in matrix sense, we have to maximize first of all the diagonal elements of the matrix. If we have two designs and we want to maximize this, so for both the designs the diagonal elements must be maximum. One is fixed 1, this other one is maximum. If we take difference, for one both is same, so this is difference is 0, while for one is if we have this optimal element is 1 a, for other one if it is b, then the difference is 0 0 a minus b, which is an indefinite matrix. So, none is better than the other. So, there does not exist any design which is Loener based in the sense of partial Loener ordering. That is why we can use this different criteria. Kiefer established this thing, D optimality criteria this, E optimality criteria this, and it can be shown that for all the optimality criteria the best design is this, that if we have our domain from -1 to +1, then the optimum design will have two support points, these are called the support points with mass half half. So, if we have n design points, n by 2 design points must be at -1 and n by 2 design points at +1. -1 +1, that is scaling and shift of origin, that is blood pressure, say 40 to 80, where to take this, or temperature in the chemical experiment, where to take this, say 60 to 80, these are the two extremes, -1 +1, that is at 60 and 80. And interested in say theta 1, the slope of the regression lines, there also we have to maximize this m2 dash minus m1 dash square, and the solution is same. For the prediction, at any point what should be the response, that is what is prediction. So, with a given design the prediction is this, variance is this, and there are, since this depends on x, there are two types of handling this problem. One is to minimize the average variance called I optimality criteria, the second one is to minimize the maximum variance. This is what is called G optimality criteria, and there is very nice mathematics, that is the contribution by Kiefer, that we can have two approaches. The one is we can reduce the class of designs. As I have said that there are infinite number of designs in a domain. We can reduce the class of designs through Carathéodory's theorem, de Lagart's phenomena, and invariance with respect to the domain as well as concavity of the response function. This is the reduction of the problem. Using these tools, Carathéodory's theorem, de Lagart's phenomena, we can reduce the class of optimum designs considerably. This is the de Lagart's phenomena. We can improve the information matrix in this way, that we can the de Lagart's phenomena says that if we have a polynomial of certain degree d, then there are d plus 1 parameters, there is no need to consider more than d plus 1 design points called support points. So, for linear regression, since alpha plus beta x we have only 2 parameters, we can confine to 2 design points, and if we stretch this to -1 to +1, then we can show that this is always the best one. So, the invariance and optimality gives this result. This is the equivalence theorem due to Kiefer. This equivalence theorem very strong. If we have intuition and the optimum design, then we can verify by this theorem whether the design is optimum in the whole class of designs or not. Not only that, this gives us the support points of the optimum design, the nature of support points, how many support, but this requires intuition, etc. For A optimality criteria, Fedorov, Russian scientist, he developed this equivalence theorem, and finally criterion function phi for any general criterion function which possess certain property, Kiefer established this criterion function equivalence theorem. This states that in the maximization problem in respect to matrix, that we are at the top of the mountain. If we take derivative in any direction, that derivative will be less than or equal to 0. This is the result. With using this result, we can find optimum designs with respect to different optimality criteria for different model. For quadratic we have this, that in the region -1 to +1, we can take optimum designs -1, 0, 1 at these 3 points. Okay. Next come response surface design. This is due to box, GEP box. There are 2 criteria, orthogonal design which estimates all the points optimally. Second one is rotatable design. Central composite design plays an important role in finding optimum designs in the second order case. And there is a third one, as I have said, which is a bridge between the two, discrete setup and continuous setup, is analysis of covariance design. These are the references. Thank you.